How are you all doing today? Very good, very nice. Let us begin with something what we started yesterday. Before I start the second topic, I just want to complete the first topic because we did not complete it yesterday. So we were talking about the, it was an introduction to coordination chemistry. So the theories that I presented, they all explain the geometry, structure, bonding, and properties of the metal complexes, molecules and metal complexes, right? So structure or call it shape, bonding, properties, and then applications of the coordination complexes is what we talked about, right? So I also explained to you why it is called coordination complex, transition metal, and all that I explained to you, right? So these are applicable to the metals. Generally, we were looking at transition metals. So in transition metals, you have 3D, 4D, and then 5D. And 3D scandium to zinc is what the chemistry of those metals is what we talked about. But in 4D and 5D, you have other metals, platinum, palladium, all that important, important metals. But if you understand the coordination chemistry of 3D metals, more or less they will be similar, but there's some differences are there because the number of electrons that are present in the case of 4D will be more than the 5D, and also they will be in different shell. So because the presence of more electrons and their positions, the chemistry also there will be slight difference. So I told you it is we were talking about the crystal field theory, which explains most of the properties, the structure, shape, bonding also we talked about, and then properties. What are the properties that we talked about? Whether is there, whether they are paramagnetic, diamagnetic, they are colored or not. See, when in the case of zinc 2 plus is a D10, which is completely all the 5 orbitals are completely filled because each orbital can take 2 electrons. So you have 5 orbitals, so 5 into 10. So when it is completely filled, it is colorless. When there are no electrons also, it is colorless, right? But again, it depends on the, what are the other groups that are present. In the case of KMnO4, in manganese 7 plus, there are no electrons, but it's still highly colored, isn't it? So color is not only because of the presence of unpaired electrons, but there are other reasons why they are colored. So I was talking about the octahedral complexes, particularly, I wanted to show you why it is called octahedron. So this is the model. Octahedron, you see, it has got 4 faces on the top and 4 faces at the bottom, and at the center you will have a metal. So each vertex will have a ligand, and that is what I was writing about manganese, for example. So let us say water. Here, this line doesn't mean that it is different from the other ones, but they're all same only. So manganese chloride is what I wrote, MnCl2 6 water. So in this case, chlorides are outside the coordination sphere. So around the metals, whatever the groups that are present, they are inside the coordination sphere. So, the two chlorides are outside the coordination. So, this is one of the examples which is an octahedral complex. This is for simplicity we write like this, but actually the but you do not see in the textbook writing like this. It is understood that if you know the chemistry, you know that the chlorides are outside and the waters are inside. So, this is actual representation, but for simplicity we write. For example, copper sulfate pentahydrate we write, very easy to write, but otherwise 5 waters inside and sulfate also inside. Sulfate is different from the water coordination. All that you don't want to represent in a simple equation or in a textbook, right? So, if you write copper sulfate pentahydrate, if you know the chemistry, you know what is the structure. So, this is a perfect octahedron. So, that means what it means is 6 waters, each water is at one vertex. So, you can see here in the center you have 4 vertices and one above and one below. So, if I invert this, I get the same shape. This is what is called, there is a presence of inversion center of symmetry. So, there is no change in the geometry, which is the case in the case of this one, manganese 2 plus, which is a 3d5. So, has 5 d electrons, and according to crystal field theory, these d orbitals get separated into dxy, dxz and dyz is what I wrote. All these 5 d orbitals, dz square and dx square minus y square, and this one is gets separated into negative 0.4 delta O, and this one should be 0.6 delta O. So, this separation should be smaller than the upper separation, but I probably have written equal separation, but through the this line I have represented that they are different. So, in the case of manganese 2 plus D5 and water is a weak field ligand, I already told you that carbon, nitrogen, oxygen and then halides. So, this is the order of the strength of the ligand. So, the strength of the ligand determines whether it is a high spin or a low spin. We have not talked about that high spin and low spin, but what it means here that the 5 d orbitals in the absence of the ligand. So, you have these 5 orbitals, you can see the 5 lines I have put in the same level. So, indicating that the energy of those 5 orbitals are the same in the absence of the ligand. So, this is metal ion only, but in practical you do not have free metal ion without attaching any ligand to it. So, in what conditions you can have a free metal ion without any ligands? In the gaseous state. Okay. So, but now in the presence of ligand, so this is Ml6 where L is here, water. So, 2 plus complex is what we are talking about, M is a manganese 2 plus. So, once the ligand is there, so there is a field which is what is called, I told you the field, it was this kind of a variation in the geometry structure was observed first time in the crystals. So, they call it, there is a field in the crystal. So, that is why it was called crystal field theory, but it is there in the gaseous phase, it is there in the solution also. So, since initially when they discovered, they gave the name and that name is carried forward. Okay. So, now because water is according to here oxygen, water is a weak field ligand. So, which is little better than the chloride, and hence chloride is not coordinating. So, chloride is a weaker ligand and hence it is not coordinating, it prefers to have water because it gives a better stabilization. So, that is what is called a field, crystal field. So, hence the waters are relatively compared to carbon and nitrogen is still a weaker ligand. So, what it means is all the 5 electrons will get occupied equally from the lower and the upper level, because the energy separation between these two are small. So that means after, according to Und's rule, of the the 3 get filled, so 4th and 5th has to go above, because the energy separation between these two levels are not much. So indicating that the other electrons cannot really come and pair here, unless this is much above where the electrons cannot really go up. So hence they don't have any choice except to come here and then get paired. But in this case it doesn't happen, because the water is a weak filled ligand. So these are called weak filled ligands, and these are called strong filled ligands, and these are called moderate ligands. So in the sense of field, that what we are talking about, the field here we are talking about is stabilization energy. So because water is a weak filled ligand, is equally get occupied, and if you calculate the crystal field stabilization energy, CFSE, I told you, you calculate negative 0.4 is what is this one, and the number of electrons that are occupied into 3 plus 0.6 into 2, which will be 0, because negative 1.2 and positive 1.2 gets cancelled. So there is, in the case of manganese 2 plus, actually it doesn't achieve anything by having water as a ligand, because it is a weak filled ligand, and there is no effect on it. Hence all the 5 ligands will be equidistant from the metal. Whereas on the other hand, if you take the copper sulfate pentahydrate, which I have told you in the previous class, so this is an example for a perfect octahedral, an example for a manganese 2 plus. So is also a good example for another example I gave you, where I fill these lower ones, and then upper ones only 2 electrons are there, but there is no unsymmetrical filling. That means the 2 orbitals that are above here are equally occupied by 1 electron and 1 electron. If you put another extra electron, then there is a problem, because one orbital gets filled by 2, another orbital gets filled by only 1, and hence that doesn't lead to stabilization. Whereas here below, both are all the 3 are equally occupied, there is no problem. So here also there is no problem. So this is an example for nickel 2 plus, which is 2468, which is 3D8. So nickel 2 plus also has a perfect octahedral geometry. So the change in the geometry happens, which is what is distorted geometry. Distortion means now the ligand on each vertex, metal is in the center. Metal is not shown here. Okay, metal is exactly sitting in the center of all these 6 ligands. Now, so if you measure the distance from the metal to the ligand, all the 6 vertices, they are all same. So there is no change. Such a geometry is called a perfect octahedral geometry. So octahedral also I told you 4 faces up and 4 faces below. So there are 8 faces, hence it is called octahedral. In spite of it having only 6 ligand, you would think why octa is coming, is because of the the faces. So now there is a change in the geometry happens whenever there is an unsymmetrical filling of this electron. For example, this will undergo distortion. This is what identified by Ian Taylor. Those 2 guys identified that whenever you have this kind of an arrangement, unsymmetrical filling of electron. So this is one example. Now I will remove electrons from here. So there are only 3 electrons. What is an example of that having 3 electrons? Which metal? Huh? It's chromium 3. Okay, chromium 3. This corresponds to chromium 3 hexa aqua complex. You can have other metal complexes also, but this is more the common, very easier for you to understand. Even other ones also you can have. So here in the case of chromium 3, you have 3 electrons and water. So this also doesn't undergo any distortion, because only 3 electrons are available, and lower level only 3 orbitals are there, and 3 orbitals are of the same energy. So, they are equally occupied. So, there is no issue at all. So, that means chromium 3 also will form a perfect octahedron, and compared to cobalt 3 plus that I talked about yesterday on Saturday, right? When I talked about that D6 system, all of them get paired because of the presence of the charge on the cobalt. Compared to 2 plus, 3 plus is because of the smaller size, ligands approach much closer, and hence the strong field they feel, since they come very close, so there is a more repulsion. See, the crystal field theory is only talks about repulsion between the metal and the ligand. So, metal is also charged, although it is positively charged, but according to theory both are charged. So, whenever charged particles come to next to each other, they get repelled. So, repulsion is more when they come closer. That is what happens in the case of cobalt 3 plus, cobalt 6 plus, where you have a cobalt in the charge is 6 plus 3 plus, cobalt 3 plus you have a D6 configuration, 3D6 configuration, and the 6 electrons all get paired. They will not go to the upper level because of the charge on the cobalt is plus 3, but if you have plus 2, it will go to the upper level. So, it makes a big difference in the having higher charge. That means smaller the size, more repulsion happens. Smaller the size, because smaller they are, they come very close to one another, the metal and the ligand, hence repulsion is more. So, in that case, I told you maximum stabilization energy. I calculated the CFSE. What was the value that I calculated for cobalt 3 plus? Huh? Negative 2.4. Negative means here stabilization actually. In the case of hydrogen atom, that when you talk about, if you calculate the energy of the hydrogen atom, negative 13.6 electron volt. If you still remember anything, so value negative here refers to stabilization energy. Okay. So, there it is negative 2.4 delta O, and here negative 1.2 delta O, because 3 into 4, right. So, the maximum that you can achieve for this configuration is 1.2, for the other configuration is 2.4, and hence in all of the chemistries that Werner talks about are of cobalt 3 plus and then chromium 3 plus complexes, because compared to chromium 3 plus, cobalt 3 plus is much more stabilized because of the double the value there, negative 2.4, double the value, and hence they don't easily, ligand don't easily get exchanged. So, this is what is called kinetic stability. What is kinetics? The reaction we are talking about, one reacting with another. So, here if you add another ligand, easily it will not get replaced. So, that is also reaction, isn't it? One ligand replaces another ligand is also a reaction. So, that does not happen because of the stabilization energy, which is what is called kinetic stability. Other one is the thermodynamic stability, delta H, delta S, all that we talk about, delta G, they are all stable. In that respect, they are all stable, but in terms of the kinetic stability, not much. So, that is decided by the value that is here. So, in the case of cobalt 3, because of the high negative value, they are very stable, they do not easily get exchanged with the other ligands in the medium. The example that I told you is if you take copper ammonia complex, which is really dark blue in color. Now, if you keep adding HCl, which is which contains water also, so it reacts with ammonia, ammonium chloride will form, then water gets coordinated. So, water is a weaker ligand compared to ammonia. So, water is here, ammonia is a stronger ligand, nitrogen. So, hence the color becomes weaker, and becomes weaker because this energy separation becomes smaller. So, stronger the ligand, this separation is higher. So, if you have a cyanide ligand, this level will be somewhere here, and if I have halides, this level will be somewhere here. So, they become weaker and weaker if you have the weaker ligands. So, that means this energy separation determines also, this is the this totally what is called delta O can be equated to energy. The energy is which is Sc by lambda. So those are all constant. So lambda can be, that means the wavelength of absorption can be easily found out. If I take a manganese complex or a copper sulfate complex or an ammonia complex, nickel complex, all that, what is that sound? Inside or outside? Oh, outside, okay. So now let us say all these complexes I take, I go to a spectrometer, UV visible spectrometer, absorption spectrometer. Then I will measure the UV visible spectrum of these compounds. Looks like from inside, outside, okay, disturbing. So now we are looking at the the color. Also in the previous class I told you, depending on how many unpaired electrons are present, whether it is a strong field ligand or a weak field ligand, you can classify that complex into high spin or a low spin. Number of spins that are present or more is called high spin. So number of spins, if they are present, unpaired spins, they are present lower, it is called low spin. So compared to cobalt 3 plus, which is a 3d6 configuration, what do you call that? What classification do you make? You call it low spin or high spin? Huh? No, cobalt 3 we talked about, cobalt ammonia complex, for example. 3d6 and the 6 electrons they all will paired, right? So they are all paired. So do you call that complex an high spin or a low spin complex? Only two, one is high spin, other. So, see, there should be high spin mean the number of spins should be that are not paired should be more, right? How many are there that are not paired in the case of cobalt 3 plus? How many are there that are not paired in the case of cobalt 3 plus? 0. There are no unpaired electrons. So hence it is a low spin complex. Okay. So this is what many times we think you have understood but not understood. That's where asking questions, which is called a interactive session. Asking questions and getting answer, now you will be able to understand better, right? Otherwise I can bring slides and simply flash through the slides and show you everything, but then you will not be able to understand. At the end of the day, even if 5% if you have understood in my 1 hour class, that is really worth it. I spent 3 hours by showing you so many slides, but if you have not understood, what is the point, right? So now before I keep this model on the table, I want to tell you that in the case of copper sulfate pentahydrate, these two will be this vertex, one vertex above, another vertex below is below. They are not same as the other 4. So you have 4 of the one kind and 2 of another kind, and this is what is called Yan-Taylor distortion, and that distortion occurs. For example, here take D4 system, that will undergo distortion because this orbital is not occupied. So this will keep shuttling between here and there, which makes it unstable. So to attain stability, get separated into 2 different levels here, and this also gets separated into 2 different levels, and now each one of them have their own orbital to have an electron equally filled. So that is where the Yan-Taylor distortion occurs. So this undergoes Yan-Taylor distortion, and this one doesn't go. I have already told you cobalt 3 doesn't go Yan-Taylor distortion because these 2 are equally filled. There is no uncertainty for it to occupy which orbital, because there are only 3 orbitals and of the same energy. If the energies are different, then it is a different matter. So that is what. So in the case of copper 2 plus, which is a D9, so I have to fill. So that is what results in which is not a stable configuration. This is D9, 3D9. There are 9 electrons I have filled. Whatever way, you have to first fill the lower one and then go to the upper one and then come back and fill the remaining ones in the lower one and then go up to the upper one, right? I simply, I put all of them, but that's how it should be done. So this one undergoes Taylor distortion, and the color is decided by the number of electrons that are present and also how many unpaired electrons are there, whether unpaired electrons are there or not there. So the color is colors of the complexes are due to what is called, one is called DD transition. So colors of complexes is due to DD transition or what is called charge transfer. So in the charge transfer you have two different kinds of charge transfer. One, it can happen from ligand to metal charge transfer or metal to ligand charge transfer, or it can happen metal to metal charge transfer. Normally, this is not talked about, that very rarely happens, only in special cases it happens, but these two are very common. So the reason for the color is two different reasons. So DD transition, that means the lower level electrons will move to the upper level when the light is absorbed, when the energy between the, I have put here, this is delta E, and that delta E is equal to H nu. H nu can be rewritten as SC by lambda, right? So lambda can be measured from the usable spectrometer. All these compounds, if you prepare complexes of one metal with carbon containing ligand, nitrogen containing ligand, oxygen containing ligand, and then halide containing ligands, then from the U visible spectrum, the lambda also will be in the same order. So and based on that order only these are arranged, and these are called spectrochemical series. So that means these are all chemicals, right? These are all molecules are chemicals, and they are arranged this, in this manner based on the spectrum that is measured, and that for agrees with what is expected. So you can easily find out that this order from the experimentally you can measure it. It is not just something arbitrarily that we memorize and then we have written here. It is all based on the facts. So spectrum can be measured and they can be arranged, and so this kind of an arrangement of the ligands is called spectrochemical series, because they are coming from the measuring the spectrum and it is a series. So hence it is called spectrochemical series. So based on all that, we can classify these complexes into high spin, low spin, they are highly colored or not colored, and what is the color in between. All that can be easily determined. So colors of these complexes is due to the DD transition. That means the electrons that are here on absorption of light, they go up, then come back to the ground state. So when they come back to the ground state, they emit light, and that light is what is seen and giving rise to color. And if they are in the visible region, that we are able to perceive the color, green, all this. You will be able to tell what are the colors, right? So these, so that means, if it is red, what it means is the energy separation between these two is small, because the red wavelength is somewhere around, let us say 700, 800, whereas the violet or blue somewhere around maybe 600. right. So, obviously because of that the energy of the violet is much more than the energy of the red. Okay. So, the and these colors arises due to the metal transition metals because they all contain unpaired electrons. If they are paired, still if they are colored, that is for a different reason, which is that reason could be due to the charge transfer. So, still some of the complexes which are having no unpaired electron are colored. So, permanganate is an example. KMnO4 where manganese is in the +7 oxidation state, there are no unpaired electrons. So, the unpaired electrons are 0. All the electrons have been 7 electrons have been removed from the manganese, right. So, it is 3d5 4s2. So, 5 plus 2 7 electrons have been removed, and that is, but this is highly colored. So, this color is due to the charge transfer, and one of the charge transfers are one of these, which one of these permanganate will exhibit. I have written 3 of them charge transfer because it does not have any unpaired electrons. So, it is not a DD transition. So, permanganate is not color, the color of the permanganate is not due to DD transition, but it is due to charge transfer. So, which one of these charge transfer is happening in the case of permanganate? Ligand to metal. Others? Metal to metal. Okay. Anybody else? Metal to ligand. Okay. Others? Ligand to metal. Okay. Yeah, it is actually due to the ligand to metal. Metal to metal is not possible because there is only one metal. But if it is in a metallic state, the metals are very close to each other. But in a metal complex, metals are far away from each other. If you take in a metal, for example, take any alloy, the metals are very close. There it is possible, but here they are not very close to each other. So, metal is not possible. There is only one metal. So, if there are 2 metals, then you can talk about metal to metal charge transfer. Here, why metal to ligand is not possible? Correct. Yeah, there is no charge anymore. Of course, manganese is 7 plus, but it only can accept electron because it's 7 plus. It is really does not have any electrons. It really likes to accept electrons. So that's why permanganate is a good oxidizing agent. So it will oxidize and gets reduced to manganese 2 plus. So reduced to manganese 2 plus means it has taken 5 electrons. All the way from +7, it has come down to manganese 2 plus means 5 electrons have been taken. So that means it is ready to accept electrons, not give any more. No electrons are there, right? So permanganate is colored due to the ligand to metal charge transfer. So what is the ligand that we are talking about? Oxygen, yeah. So, manganese, permanganate so it has a tetrahedral geometry. So, normally how you write is not the way to write. So, tetrahedral geometry means so that is the permanganate. So that means oxide is a ligand. So how do you obtain oxide ligand? Where is the oxide ligand coming from? Water, correct. So in water you remove one nitrogen, so this will become 1 minus. Remove another hydrogen, it will become another minus. So it is O2 minus, right? It is an oxide ligand. So that oxide ligand is now we talked about water as a ligand. Hydroxide can also be ligand. I removed only one proton, then it is OH minus. So it is a hydroxide. That also can be ligand. When I remove both the protons, then it is an oxide, is a ligand. So this is also in the case of permanganate, it is a oxide ligand. So oxide has a charge, and manganese 7 plus ready to accept electrons. So the charge from the oxide to manganese 2 plus happens. So it is not a chemical reaction, there is small amount of charge that gets transferred. But if you keep permanganate in water, slowly you will see it get reduced to MnO2. So it's due to the reaction. So in fact it easily gets reduced to MnO2. Okay. So charge transfer happens. Because of the charge transfer, this permanganate is highly colored. So the DD transitions are not highly colored. How do I determine the strength of the color? One permanganate I say is highly colored, whereas copper sulfate pentahydrate I say it is blue in the solid state. But in the solution, let us say I prepare 1 mole of solution of copper sulfate pentahydrate, and also I prepare permanganate also 1 molar solution. Why do I say 1 molar? Number of molecules present in both the cases are same, isn't it? Avogadro number of molecules will be present. If I prepare 1 molar, so Avogadro number of molecules in both the cases, when you have same molecules you can compare, but if you have different concentration you cannot compare, correct or not? So if you prepare 1 molar of permanganate and 1 molar of the copper sulfate pentahydrate, and if you compare them, now I take from that 1 molar, I take 1 drop and put it into 1 liter of water of the copper sulfate, and similarly I will take 1 drop from the permanganate and put it into 1 liter of water. In the case of permanganate I still see color, but in the case of copper sulfate I feebly colored, you will not be able to see. So it is because permanganate is highly colored, it still maintains, in spite of having same number of molecules, it is still colored. Permanganate you would have seen, even if you take very small amount and dilute it, it keeps giving the color, pink color, right? So the strength is determined by the, so that is what is called, there is a in spectroscopy, it's called epsilon. A is equal to epsilon Cl is there in Bees-Lambert's law. Some of you, I don't know whether you have Bees-Lambert's law is there, I think. You have read about it, right? Where A refers to absorbance, E, epsilon refers to strength of the color, and C refers to the concentration of the solution. L refers to the path length. So that means, if I take a test tube of the, let us say it is 1 centimeter path length, I am passing the light, so it has to be, path length also has to be same. So keeping all that in, constant, so concentration is constant because both of them I said 1 molar, right? So now I am measuring absorbance, it will be different for copper sulfate and permanganate, because the one that absorbs strongly, which is permanganate, will have a very big absorbance, whereas the one that having lower absorbance will have a lower, and that's how I find out. So this epsilon is equal to A by Cl. So this is what is called absorption coefficient, which represents the strength of the color. So I can easily find out, and you can, given I give you permanganate and then I give you copper sulfate, you know the molecular weight of both of them, so you can calculate now 1 molar concentration, right? So whatever is the molecular weight of copper sulfate, that molecular weight in 1 liter will give you 1 molar. So similarly, permanganate molecular weight, that same weight in 1 liter will give you 1 molar concentration. So now if you measure the spectrum of these two compounds, you will be able to measure the epsilon, and in the case of which is the strength of the color, right? So permanganate I told you is highly colored, whereas copper sulfate pentahydrate, in the solid they are colored, highly colored, but in the solution we are talking about. So in the solution, where you can easily determine the real strength of the color of these compounds, and they can be easily measured by the spectrometer, and the epsilon can be calculated. In the case of copper sulfate pentahydrate, epsilon of copper sulfate for KMnO4 will be, let us say, is around 5000, whereas the same epsilon for copper sulfate pentahydrate will be around somewhere 100. So clearly indicating, so epsilon for what copper sulfate pentahydrate will be 100. So clearly now you know that this is 50 times greater than the color is 50 times greater than that of the permanganate. So that's how you determine, and always the complexes having tetrahedral geometry will be highly colored, and permanganate is one that is having tetrahedral geometry. So I did not talk about the tetrahedral geometry, I only talked about octahedral complexes. So tetrahedral complexes, this is permanganate is one of them. So the tetrahedral means 4 faces. So you can see this is the model for a tetrahedral complex. It has 4 vertex, right? So 4 vertices are there present, and each vertex will have one ligand, and center of this model will have a metal. So you can see I have this model, right? I invert it by 180. I don't get the same picture. The reason, the sharp end that is was here, now this has a flat end, right? Earlier it was here, so I should get the same picture. That means this should have been here, which is not there. So in the case of tetrahedron, there is no inversion center of symmetry, and same theory what we talked about in the octahedral complexes can be also talked about. Let me just briefly write. So the same 5 orbitals now get split into so what was below goes above. Okay. Huh? Oh, I'm sorry. Yeah, should be down here. Yeah. No. It's correct only. Okay, it's correct only. Okay. So lower level 3 are there, upper level 2 are there. So if I invert it, so upper level will be 3 and lower level will be 2. So this will be called E, this will be called T2. The reason why G has been removed, because G refers to inversion center of symmetry, and this one doesn't have inversion center of symmetry. So hence that the symbol G has been removed, indicating that it is there is no inversion center of symmetry. Okay. So and this is for the tetrahedral. So that means whatever I was writing where L is halides generally. Halides is chloride, fluoride, bromide, then iodide. Okay. So that is the order of the strength of the ligand. So fluoride is stronger than the chloride, chloride is stronger than the bromide, and then bromide is stronger than the iodide. So among them, fluoride is the strongest ligand. So since these ligands are all weak field ligands, so that means the energy separation between these here, delta T will be almost 45% less than the octahedral. So 45% less than the octahedral, because the energy separation between the upper level and the lower level is small, because they are weak field ligand. So when cyanide is a ligand, these two level will be somewhere here, because carbon containing ligand cyanide which is a strong field ligand, right? So hence whenever, so now this delta O, that what is here, will be there. So energy separation will be very high. So what happens to the lambda? Lambda will decrease. What will be the, let us say in terms of 800 and 200 for a cyanide, do you put 800 or 200? You understood the question or not? No? So, in which case lambda, let us say I gave you two values 200, 800. So, where do you put 200 and where do you put 800 between these two here? Huh? 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 So, 200. So, 200 is the left hand side, 800 is the. How many of you agree with all that? It's like in the assembly, they look at others whether they raise the hand or not. So, 800, 200, but you did not raise your hand, No, I asked which one is 800, which one is 200. Yeah. So, this is this is 200, is it? Because higher the wavelength, lower the energy, right? Look at the here, the separation is too much. So, that means this will be somewhere in the UV region, this will be in the visible region, right? Depends on the unit, frequency if you put, then it will be different. Okay. So, and if you look at the tetrahedral complexes, because the energy separation between the two levels are almost the same, not too different. So, hence the tetrahedral complexes are always high spin complexes. That means they do not get paired, because the upper level and lower level of the same energy, electrons like to go to the upper level also. So, hence it leads to high spin complexes. So, tetrahedral complexes are always high spin, and not only that, I told you permanganate. So, permanganate has what kind of geometry? Tetrahedral, because it has 4 ligands, right? 4 ligands and 1 metal, and that is what I have written here. Ml4 2 minus, for example, metal is 2 plus I, manganese 2 plus, nickel 2 plus, copper 2 plus, iron 2 plus, cobalt 2 plus. They all form this kind of a complexes with chloride as a ligand, where L is a ligand because I have put here ligand, right? Often chloride is the ligand, it is present, because in nature chloride is what is often observed. Sodium chloride is plenty of present, right? So, bromide and iodide or fluoride not readily available, but they are present, but not so much. Abundance is more for chloride, and hence often we talk about chloride complexes, right? So, delta T is 45% less than the delta T, delta O. Delta T, whatever that I put is right, should be the other way, right? So, it is 4 by 9 delta O. Delta T is equal to 4 by 9 delta O. So, that means is almost 50% less than. No, 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 no. It's 50%, you know. So is 50% of delta O. That means is less than delta O, right? So that is approximately is what I have put. That is the actual number to be calculated. Okay. So because of that, energy separation is small. Always tetrahedral complexes are high spin in nature. Okay. And the whenever there is a presence of this letter G means the transitions that can take place are forbidden. That means, let us say this electron going to this level gets forbidden because of the presence of that inversion center. G is represented by the inversion center. Okay, so gets forbidden. If there is no G, there is no, so that means easily transition take place. That is one of the reason why permanganate there is no such restrictions for it to take transitions. In the case of tetrahedral, easily these transitions takes place, and there are other rules to find out. The strength of the color can be determined by other factors. There are selection rules. Selection rule means when do you say that the electron is getting excited to the upper level easily, or when do you say it doesn't get excited to the upper level easily. So there are selection rules. So the selection rules are spin selection rule. That means so let us take this as an example. Okay. The total number of spins that are present is 1, correct? So if I excite an electron from here and take the electron there, so again what is the total number of electrons present? 1. So there is no change in the spin state. So this is spin allowed. Okay. So whenever there is a change in the spin state, when does it happen? Let us say, let us take a D5 system, okay, 3D5. So this is the ground state. So now I have excited an electron from ground state to this excited state, right? What is excited state? Because it has absorbed energy and the electron has gone up. I can I can excite this electron, but I have taken that. I can do this also, right? So now there is a change in the spin state. Number of unpaired electrons that are present here is 5 by 2, right? Each spin has half. So there are 5 of them, so 5 by 2. And here is only 3 by 2. So if I do, so this is also S. So delta S will be not 0. Okay. So in the case of copper, the delta S, because the number of spins in the beginning is 1, number of spin after exciting is also 1. So the S is equal to half, S is equal to half. So delta S will be, it will be 0, right? Because there is no change in the number of spins. And in this case, there is a change in the number of spins, because what was 5 became 4. Because if I excite electron, where will it go? It has to go sit somewhere, it has to get paired. So now it has got paired, a number of spins get reduced from 5 to 3. So delta S is not is equal to 0, right? So in such a case, it is called spin forbidden. Okay, this is called spin forbidden. So there are many So, these are the selection rules that they have to follow for them to absorb light. In the case of permanganate, if you take Mn2 plus has no number of spins. There are no unpaired electrons in the, no, I am sorry, in the permanganate. There are no unpaired electrons. So, that spin selection does not arise at all, is not it? And also in this case, for example, in the case of manganese 2 plus, which is an octahedral complex, I told you, Mn2 plus Mn Cl2 6 water. So, 6 waters are there, it is a octahedral complex. So, here I have to write that T2G and Eg. So, here also that T2G and Eg is there. So, whenever a molecule is centrosymmetric, the probability of transition is less. Whenever it is distorted, now probability increases. So, that means if it has a perfect geometry, it will not easily get excited to the upper state. But distorted one, so now there is a change in the energy, because the distortion in geometry, there is change in energy. So, partially whatever is forbidden becomes allowed. So, here according to this it is forbidden. If it has a distorted geometry, partially it becomes allowed. Okay. So, in the case of MnCl2 6 water, in fact manganese 2 complex is almost no color, very pink color. You go check in the lab, very pink color it will be in the solid state. If you put it in water, no color at all. So, it is because of the spin forbidden and also what is called symmetry forbidden. So, that means symmetry means it is highly symmetric, then it will not become the transition will not be allowed. If there is less symmetric, then transition gets allowed. So, because of these two reasons, the Mn2 plus 6 water, which is an octahedral complex, is feebly colored. So, there are some of the selection rules you have to apply. So, if you apply that, you will come to know that in the case of MnCl2 6 water, which is an octahedral geometry, almost no color, whereas permanganate has no unpaired electrons. So, that the spin selection rule now is not applicable, because there are no spins at all, because Mn7 plus no unpaired electron. So, 0 unpaired electrons, so spin selection rule does not apply. And also in the case of, because it is a tetrahedral geometry, that G is not there. So, once G is not there, so it becomes allowed, which is what is called symmetry forbidden and symmetry allowed. So, symmetry means you saw an octahedron is highly symmetric, whereas tetrahedron is not highly symmetric. If you compare to these two, that is highly symmetric. Number of symmetry elements that you can find out. Symmetry, if you have studied, that will have more number of symmetry elements compared to this. So, that means highly symmetric. Okay. So, highly symmetric means less number of probability for it to have a transition. Transition means electron has to go from the, when light gets absorbed, electron from the ground state will go to the upper state and it comes back to the ground state. When it coming back to the ground state, it releases the energy, and that energy, if it is in the visible region, you see the color. If it is in the UV region, you will not see color, right. So, these are some of the reasons why they are colored and how you explain the color, and why that energy separation between the lower level and upper level changes because of the presence of these ligands. So, ligand, so spectrochemical series you have to know. So, ligand determines the energy separation. Charge also determines the energy separation. Charge means instead of +2, if I have +3, smaller the size, more the repulsion, and hence stronger the field, right. And also position of the metal in the periodic table. That means 3D, 4D and 5D. So, that crystal field stabilization energy, if you go from year to year, 50% more increases compared to the above, and here it increases 75% more, because more electrons are there. Okay. So, that means if this was 100%, this will be 150%. So, this will be 175%. So, that means as the as you go from 3D, 4D and 5D, and hence most of the complexes from the 4D and 5D are all low spin complexes. because the crystal field stabilization energy is so high that this energy separation between the lower level and upper level is very high. So they get paired. So get paired means no unpaired electrons. No unpaired electron means it is low spin complex, right? Number of spins are less is what is called low spin. Number of spins are more is what is called high spin. So these are the reasons: ligand, spectrochemical series, charge on the metal, and position of the metal in the periodic table. So in the 3D, 4D and 5D, and also going from the left hand side to the right hand side also, the crystal field stabilization energy increases because number of, because you are adding electron to the same shell, so charge increases. So as the charge increases, I told you from +2 to +3, I told you as charge increases, crystal field stabilization energy also increases. But going to the next level, it is in a different orbit, level, right? K shell, L shell, all that we talk about, right? So it is in a different shell. But in the 3D, it is in the same shell. So that means you are keep adding 1, 2, 3, 4, 5. The atomic number increases, charge also increases. So as you go from the left hand side to the right hand side, the crystal field stabilization energy also increases. So these are all some of the reasons why the stabilization energy is very high, and why they are stable, and the way they behave also will be different. If you have understood all this, you will know how the chemistry works for all these metals. You have to read. Okay. So I complete on this part. Probably not much time, but I still talk about the role of metal ions in biology. That is other topic I wanted to cover, but since I did not finish, there is no point in leaving this somewhere halfway and then moving to the other topic. Okay.
SwayamPrabha, Digital India, Educated India.